Alright, welcome back to our Computational Topology tutorial series. And today we're going to be just making a simple vector class, which will be analogous to the matrix class we made last time. So let's see. Well, I know that I'm going to basically use the same stuff that I have here. So let me just copy this. And I'm going to make a new file, vector.h. And of course, right, this is going to be templated. Oops. Class vector. And well, we'll have our usual default constructor here, and then the destructor. And then I want a constructor that actually takes in a std vector, which is basically going to be the element, the member here that we're actually going to use as our vector. Well, I want a couple other things. So I know that std vector, of course, keeps track of the size, but I want to put this in its own member, its own element, even though this guy has a pointer that keeps track of the size anyway. I just want to keep it here as well. And so we have our regular vector, and let's see, that's pretty much it for the basic stuff. Now let's just make a getter for the dimension. Right, I just want to return a copy of that. So, and then everything else is, well, most of everything else is going to be operator overloads, again, just like with matrices. So I'll have my usual access operator. So I want to return the a copy of the value using the parentheses and some index, and of course we'll have to error check this so that I is not bigger than the actual size of this guy. But this one returns a copy of it, and I also want to be able to return the reference so that I can change it using these brackets, which is that one, right? And so this is basically the same thing as here. Right, of course, this has two indices because it's a matrix, and this one just has one. Now, the other thing we can do with vectors, of course, is add them. So I'm going to overload the plus operator, and just like with matrices, I want to return a new vector that's the sum of the original, but I don't want the originals to change. I want them to stay the same. So that's why I got these consts here. Likewise, I can always add to the particular vector that I'm talking about rather than make a new one, and that is just going to use the void. It's not going to return anything, and it's going to use the plus equal rather than just plus. And again, I don't want to change the other vector, I only want to change this one. So still want const there. And we have exactly the same thing for subtraction. So I'm just going to copy and paste that. And this becomes minus, and that's minus. And then we have various products that we can use with vectors. The simplest one is just a scalar multiplication. And so again, I have two types of these. One in which I'm going to change this to star. One in which I take a vector, multiply it by a scalar to return a new vector, or one in which I multiply the current vector by a scalar. And so I change the one I'm interested in rather than make a new one. Okay. And let's see. I also want to be able to compare two vectors. And I'll have to add this to the matrices too, because I want to be able to compare two matrices as well. So this is going to return a bool, true if the vectors are equal, and false if they're not. And so I'm going to overload the equals equals sign there, and again passing a reference to another vector, leaving both of these the same, not changing them. Okay, and then we have what's called the dot product, and the dot product is defined such that take two vectors and multiply them in a certain way to return a scalar. Right, so this doesn't return another vector, it returns a scalar. And so again, I don't want to change the two vectors. I just want to manipulate them and manipulate their entries to return this scalar value. In addition to all that stuff, since we have this dot product defined, there's another quantity that we can define in this vector space, which is the norm. And that's just the length of the vector. Right, so this will return the length. And so I'm just going to add it here as another element of this class. And this will just store the length of the vector. So I need some functions for actually computing it. So one of them is going to actually fill this value with the length, right? So this won't return anything. It'll just actually, given the entries in here, it will find the norm and return it. And then I want another function that will take that norm and divide all the components of the vector by it, thus making the vector into a unit vector. And that way, when I take the dot product, I get 1. Now, this what it means to be a unit vector. And so I can always do that by dividing by the length. Okay. And then, let's see. Oh yeah, I want to be able to retrieve it too, of course. And this won't be just a simple return because, well, it may not exist. It may not be stored here. And so I only really want to calculate it when I need it. I don't want to do it every time I make a vector because I may not care what the length is. And so instead of just doing a getter for this m norm, this actually has to be a little more complicated of a function. And then in 3 dimensions we have, well, 3 dimensions and 7 dimensions. But yeah, who cares about 7 dimensions? This maybe a string theorist does, but so this cross product is defined in 3 dimensions. It comes up often there, and so we may need it, we may not, but whatever, we'll put it in just for the hell of it. And finally, we have a projection. Right, so if we have 2 vectors and we want to project one onto the other, this will return the component, or the vector, the piece of that vector that is parallel to the other one. So we'll see what that means when we get there. But that will be important. for certain things. All right, so that's everything. Now we just have to define all these things. And so the way I'm going to do it is, well, let's just go through one by one. And, you know, of course, all these declarations need template type name T before them. And the default constructor, I'm just going to set the dimension to 0. That way we don't run into any problems in case we ever create a vector using this. Because, well, then if I go in and I try to figure out, or I use this get dim, right? If it hasn't been set to 0, it could be, you know, some other value, and that's going to screw everything up potentially. So I'll just set it to 0 if I use the default constructor. And then, of course, for the destructor, that'll just do nothing. And then I have this one in which I actually pass in a vector. And let's see, what do we want to do here? Well, I could just do this and be done with it. But this isn't very memory efficient, because what this is doing is actually creating a copy of this. And I don't want to do that. And so instead I'm going to use std move. And that's actually going to, you know, not create a copy. It's just going to assign the pointer to this object, the actual stuff that's here. Right, so it doesn't create a copy. It just changes ownership. And if I do actually give this a vector, well, then I can define the dimension to just be the size. Okay. Right. So now on to the actual operator overloads. And let's see, we have addition first. In particular, we have what do we have? No, we have the access operators first. So we want to return a copy of element T that exists at index I. And so we need to do some type checking here, because we have to see whether or not this index I is out of bounds of this vector. And so if that is the case, then I guess for now we'll just print an error. You know, eventually we'll have better type checking for this. But for now, this is fine. So I'm just going to say, alright, if you try to access this, I'll tell you what the actual dimension is. That way you can, you know, figure out why it didn't work. And then I'm just going to return whatever's in the first entry. Now I know that this could potentially cause issues as well, because if I did create my vector using this, then this will be empty. And so this will give me a memory error. So, yeah. I guess what I could do is just return 0. I think that that's fine. Although that might give me an error, because we're using a template argument. Let's try it and see. Maybe it'll work. If, you know, it isn't out of bounds, then I'm just going to return that, the actual object there. And this is unsigned, and so I don't run the risk of putting a negative number in here, so this is good. This is fine. Alright, so that's that one. And of course, the one that returns a reference, that's the same exact thing. The only difference is I have a reference here, and it's not const. Other than that, the function will do the same thing. Okay, now we get to the addition. Okay. So here, because we don't want to actually change this guy or this guy, we have to make a new vector and populate it with, you know, whatever operation we're doing with respect to these two guys. Yeah, that's going to be the only way it's going to work. So, of course, this will only be defined if the dimensions are equal. Right, if the dimensions are not equal, then what do? Well, we have to do something, because this is supposed to return a vector. So we'll just set this temp equal to the current vector. And yeah, we should have some kind of error here to let us know that it failed. And I think that's going to be fine, just to say that, because I think every time we run into this issue, we're going to do exactly the same thing. We're just going to return whatever this is. Unless the function returns void, then we're just not going to do anything. But this will basically signal that, you know, we tried to add or subtract two vectors that were not the same dimension. And so whatever we returned, we can expect it to be this, the actual vector of the current object. If it does work, then we need to actually go over all of these values and add them to the vector. In particular, we're going to add the sum of every component, and that's going to be the new components of the new vector. And once we have that, then we can just return with, you know, sending this guy into this object. Okay. Now, this is going to be similar for the one in which we just append the current vector, so where this ends up being void, and this is not const anymore. The only difference is we don't actually have to do this, and here we're just going to say return, right, if it fails. So nothing's going to happen. Oops, this should be plus equals. Down here, we don't have temp, and so we're just going to say vec plus equals the other one. And again, we don't have to return anything there, so there we go, right? So this one, we're just adding the other vector's values into our components, and that's it. Subtraction is exactly the same, right? It's just swap everything for a minus sign. We got minus here, minus there, and minus there. Okay, and that was easy. Let's see, what else do we have? Well, we have scalar multiplication, and that is also going to be similar to these two. So copy and paste those again. Let's see, only this is going to be star, that's going to be star equals, and these are both going to be just scalars. And you know, fortunately with this, I don't care what the size of any of the vectors are, so I can get rid of this whole conditional block here. And this is going to be just multiplying that scalar. And here, also I don't care about any of this. And instead, this is going to be times equal scalar. There. Alright. Then we had this Boolean operator to check whether or not they're equal. So let's see, how are we going to do that? So operator equals equals, and let's see, we want, yeah, again we have to check. If the dimensions aren't the same, then they're obviously not equal. So if that happens, we're going to return false. Alright. Yeah, so that's going to return false. And if that doesn't fail, then we actually have to check every component to make sure that they're all the same. That's what it would mean for the vectors to be equal. So here, for each one of these, I'm going to check. If they're not equal, then return false. And if it makes it all the way to the end, then they must be the same. And so I'm going to return true there. Okay. Alright. Now, what did we have? Dot product. Okay. So there's another one in which the vectors have to be the same dimension. Otherwise, it's not defined. So, let's see. Yeah. Right. So, just like with the addition, I'm going to have to keep track of this value separately here. And I'll just call it dot, this return value. And I have to see if these guys are not the same dimension. I want to do basically the same thing I did before and just say error vectors are not compatible. And that'll be fine for now. We'll make that better later. And I'll just return 0 for the length. Right. Is this going to cause problems? I don't think this will cause any issues, provided that we're not dividing by this value. There are situations in which that may happen, so we'll have to worry about that when we get there. For now, I'm just going to leave this. Let's see. So, if it does pass, then I just calculate the dot product, which is just the sum of the components multiplied together. And that's it. And there we go. Simple enough. Okay. And then we have our normalization functions. And so, let's see, what do we want to do here? Well, the first one was find norm. So we want this function to assign our element norm with the actual value that we're going to compute. So the norm is basically just the square root of the dot product of the vector with itself. That's the length. Right, so it's only going to be 0 if the vector is the 0 vector to begin with, because you're multiplying it by itself. So I'll just do this explicitly here. I could call dot product the dot product operator, but I'm just going to do this. And then I'm just going to set the norm equal to the square root of that value. And there we go. That's the length. And then I want to be able to actually divide by this value. And so that's going to take a little care, because I want to make sure that I don't have the 0 vector. That's something I definitely want to avoid. That'll cause an issue. And so the first thing I want to check, though, is if the norm has actually been calculated, because I don't want to do it twice unnecessarily. And so only if it hasn't been calculated do I want to actually run this function to find what it is. And if it turns out that the norm is equal to 0, then, well, I should just not do anything and say the vector is the 0 vector. And so, therefore, I can't divide by its length, as that would be dividing by 0. So I'll just return in that case. If, on the other hand, it happens to work, then I'm going to go through and divide every element by that norm value. Okay, there we go. Yeah, so that's it for that. Finally, we have our getter, and that one, I didn't want to just write, hey, send out the norm, because we may not have calculated it yet, because I may not always want to calculate it for no reason. So again, I'm going to check if it hasn't been calculated, then go ahead and do it, and then return. Right. But don't do it unnecessarily, because I may have done it already, and so I don't want to have to do the calculation twice. Okay. And at this point, we only have a couple more functions to do. The one is special case, whenever our vectors are in 3 dimensions. And so there, we have this product called the cross product, and that actually returns another vector. And so, again, we're going to have to create this temp, right? Because I don't want to actually manipulate the values in here. Now, I have to check if the dimension of each of these is not equal to 3. So if either that one's not 3 or this one's not 3, then this is invalid. And so we just want to say error cross product not defined for vectors of dimension mdim. Actually, that may not. That may sometimes give us an answer which is wrong, because this could be 3, but this could be something other than 3, and this error would still happen. So I guess here I should just include the other one. Yeah. Just to avoid confusion. And if that happens, again, we want to set temp equal to the current vector. So you got to set it equal to something. And then return it if it ends up, not working. But if it does work, if they are both 3-dimensional, then we just have an explicit formula for the components, the new components. And that's going to be the y component of this times the z minus the opposite. So the z times the y. And then for the new y component, we have the z component of this one times other x minus this x times other z. And then finally the z component is x times y minus y times x. Bam. And then we just return whatever that is. There. Okay, cool. So then we just have one more function, and that's the projection. Right, so this is going to project, or it's going to return the component, the vector that points along the direction of some other vector. That's what this is going to do. And this will be useful for things later. So again, we need this guy, and we want to set, I think at the beginning, we want to set whatever this is equal to mvec. We don't have to do it that way, but it's just the way I'm going to do it. So again, the dimensions have to be the same, otherwise it's not defined. And so that's that. And if it happens to be fine, then we have to do a series of multiplications. So the first thing we need is the dot product between the two vectors. So in order to compute that, I'm going to say that t dot is equal to, I'm just going to use the dot product multiplication by sending this actual this vector and the reference to the other one. Yeah, there. And then I need the norm of this vector. Actually, I need the norm squared, not the norm. So I could do that using the normalization functions, but it's just quicker to do it this way because it is just the dot product of the vector with itself. And then I'm going to divide this value by this value. So I'm going to divide whatever this ends up being by norm s. And then I'm going to multiply that by all of the entries of the current vector. And that will, adjust the components of this such that it's projected onto the other vector. Again, I'll explain all that stuff in another video where I actually go over the theory. But for now, that's all it is. You're just multiplying by all those. And then, of course, I have to return this. And that's it. That's everything. So I want to test this now, and I'm just going to make a temporary print function just like I did before. And in fact, let me see here. I could probably just steal whatever that print function is. Yeah. And just change this vector. And I don't need the inner loop, so I'm just going to do that. Yep, I don't have to do that either. Just have to do this. And mmat is actually mvec. Just one index. and this will be empty. There we go. So now let's go back to our main, and so we can test this out. So I'm just going to get rid of all this, and I want to check a few of our operations here. So, well, let's just make sure that this will actually compile, so I don't have any issues. So if I go here, okay. Good. All right, so no errors. And then I'm just gonna test out various things. So I'm gonna make a vector, and I'm gonna pass into it this array. Let's see. I'm just gonna use the unit vector along the x direction. And let's see what happens when we print that. Good. Right, so it did what we wanted. Okay. Now let's see what happens with addition. So I want to make another one of these. Call it V2. And let's see. I'll make this one along the y direction. So it's the unit vector in the y direction. I'll print that one again. So, and then I want to make a third vector, V3, which is V plus V2. And then I'm going to print it. So let's see what happens when we do that. Bam. Exactly what we want. This plus that is that. Good. And if I replace this with subtraction, should get, yep, that minus that, 1 minus 1. Okay. Now let's see what happens when I multiply by a scalar. So that's going to be this, 6.0. I'll just put F here. Yeah, just leave it like that. And I'll print it again. Yep, so that worked. Multiplied everything by 6. Good. Let's see, what else do we have? The cross product. So, just because we're in 3 dimensions, I might as well do this. So I want the cross product between V and V2. That's what this should return. And let's think about what that would be. So that should be, it should just return the Z unit vector. Right, it should be 0, 0, 1. That's what I should get. So let's see if that's what happens. Yep. Cool. So we know that works. Let's see. Oh yeah. Finally, I want to test the projection. So I want to project V onto V2. I want to know, what is the amount of V1 that points in the direction of V2. I want to return that vector. So that's going to give me this, and it should give 0 because this and this are orthogonal. So let's see if that's what we get. Yep. Yeah. So there's a precision error here, and we could probably clean that up by having some kind of cleanup function that gets rid of these. Right, because that's obviously 0. E to the times 10 to the minus 310. That's just a precision problem with the dot product. So that works. And what else do we have? I think that's pretty much it. So I think that's going to be it for now. So next time we'll actually start implementing some of the algorithms in the book using our matrix class. So hope to see you then. For now, bye.